Hello, everyone. It's Mrs. Tiller here. We're going to start the video for 6-3 logarithms. What I'm planning to do is do this as one whole video, but I'll suggest where to stop in the middle and do part of your problems and then continue the video and do the rest of your problems. Okay? So as you can see at the beginning here, what we're looking at is a real-world application of logarithms, which are earthquakes. You all know, even though we don't live in California, we live in Florida, where we know more about hurricanes than earthquakes. We know that, for example, in California, if we hear about an earthquake there, that it's measured on the Richter scale. And the Richter scale is an example of a logarithmic scale. And it's a scale where we're basically solving for the exponent in an exponential equation. So let's start by looking at this example. We'll read it together. Earthquakes make seismic waves through the ground. The equation y equals 10 to the x relates the height or amplitude in microns of a seismic wave y and the power or magnitude x of the ground shaking it can cause. Now, this magnitude x is actually what will be the value of the logarithm. So let's look at this for this particular table. We're looking at the table here. I'm going to write this equation y equals 10 to the x above it. And you'll notice here we have a missing value of x here. And if you kind of do some testing here, you'll notice we've got the amplitude here is 100. When the value of x is 2. So let's look at that. We've got 10 squared equals 100. And that, in that case, x is equal to 2. Here we've got 10 cubed is equal to 1,000, and there x is equal to 3. Then we jump down here, we see 10 to the 4th power, it's 10,000, and x is equal to 4, okay? But you'll notice here, we don't know what the magnitude is, we just know what the amplitude is of that seismic wave. And of course, what we can do, is we could write an equation and we can kind of make some guesses about what that value of x is. For example, we can do that up here. If I have y equals 10 to the x and I let y equal 5,500 equals 10 to the x. We can kind of maybe do some trial and error, for example, on our calculator, and see what power of 10 will give us that particular value of y. But what we're going to be learning about in this section is a way where we can actually solve directly for that x without having to do it by a guess and check procedure. Okay? Meanwhile, we can just look at two individuals here, Taylor and Chen, and look at how they solved it. Presumably, maybe they didn't know about logarithms. And Taylor had one method. He looked at the table, and he noticed that 5,500 is halfway between 1,000 and 10,000. And he also recognized then he could maybe consider the same pattern and know that 3.5 is halfway between 3 and 4. So he guessed that the value here was about 3.5, okay? And remember, if we're talking about halfway between, we're talking about the average. For example, if I added up 1,000 and 10,000, I get 11,000 divided by 2 would give me that 5,500, right? Then we can look at Chen's method of figuring this out. With Chen, he recognized the same as we did here. 10 cubed is 1,000, 10 to the 4th is 10,000. And he decided, he would kind of try to get closer and closer to the correct value of x. He tried 10 to the 3.5, just like Taylor did, but he decided that wasn't close enough, okay? So he realized he actually worked it out and got only a little over 3,000, which wasn't big enough. And then he tried a little bit larger exponent. He tried 3.7 as an exponent. Still wasn't big enough. And he tried 3.8 and he realized, oh, too big. And then he found a value in between, but a little bit closer to 5,000 because 5,500 is a little closer to 5,000 than it is to 10. And then he came up with a magnitude of about 3.74. Okay, So you'll notice here, these are kind of, you know, a little bit more complex ways to do this, and it'd be a lot more direct to have a direct way to solve for x, and that's what we're going to learn about in this section. But using this pattern, at least we can kind of get an idea of what method they were using. What's the magnitude of an earthquake with amplitude 100,000? How do we know? So I'm just going to, you know, take a pause for just a moment, just so to give you a moment to think about it. If we look over here and we kind of look at the pattern here, okay, and you'll notice here with 3 zeros, we're 10 cubed, 4 zeros, we're 10 to the 4th. So of course here with 5 zeros, that's going to give us 10 to the 5th power. And so we know that the magnitude here is going to be 5. In other words, what that is 5 on the Richter scale. Okay? So let's just consider both of their arguments, Taylor and Chen's. Is each method valid, and could either method be improved? Okay? So what do you think about that? I think, you know, if you notice these values over here, that of course Chen was a little bit more precise, right? So both are valid methods, but Chen was just a little bit more precise, okay? So both valid, and Chen was more precise, you know. Could either method be improved? Maybe Taylor could have tested, you know, Taylor could have checked. (10 to the 3.5 and realized it was too small. Okay. All right, so let's look a little bit more at what a logarithm is, and we're going to do that by first just reviewing a little bit about exponential equations that we had done before the spring break. Okay, so let's just look at these two equations here. We'll notice here, of course, 2x equals 8. We hopefully all recognize that that's a linear equation. And 2 to the x equals 8, of course, is an exponential equation. And to be able to solve 2x equals 8, it's pretty straightforward, right? You can just use opposite or inverse operations. And of course, division is the inverse of multiplication, so you can divide both sides by 2, and you can easily solve the equation, and you can see that over here, okay? But when you're dealing with 2 to the x equals 8, you have to be really careful there, because a lot of people will have a tendency to do the same thing and dividing by 2, but you have to realize the opposite of raising 2 to a power is not dividing. So we need to figure out a way to do the opposite of raising to a power, the inverse for exponentiation. And what we're going to try to do is figure out to what exponent would we have to raise the base 2 to get 8. And that's where a logarithm is going to come in, okay? Now, obviously, mentally, many of us, as we'll see in a moment, could figure out what the value of x is just from our background knowledge. But when we get to more difficult problems, we want to be able to solve them easily, and that's where logarithms come in, okay? So basically, the inverse operation to exponentiation or exponential functions is logarithms or a logarithmic function. And what we're going to learn how to do is how we can write the exponential equation 2 to the x equals 8 as a logarithmic equation here, okay? And what you'll notice here is if you kind of look carefully at this notation, you'll see that 2 is the base of the exponential function. And if you look here at this notation here, 2 is basically below the other values. It's the subscript, or it's in the basement, if you think of it that way. So in both of these cases here, 2 is considered a base. Okay? So log base 2 of 8, as you can see, It's written log base 2 of 8, log or logarithm base 2 of 8. And solving this gives log base 2 of 8 equals 3 because 2 cubed equals 8. Because basically here what we have to understand is the value of the log is the value of the exponent. So essentially when we're dealing with a logarithm, we're solving for the unknown exponent. So the log is the value of the exponent. Okay. Let me just pause. I'm just going to make sure we're recording and then I'll continue the video. It looks like actually we're in good shape. Okay. So we're going to be looking at requirements, certain values, you know, whether it has to be positive always, what restrictions there are on the value of further, for example, b cannot equal 1, and also x has to be positive. But we'll be seeing that more within the example. Okay, and we'll also kind of understand a little bit better how to change between logarithmic and exponential form a little bit in some of the examples in a few minutes. Okay, so let's turn here. So we have a summary here. See if I can zoom in a little bit on that. So we have a summary of the difference between exponential and logarithmic form here. And as you can see, it's color-coded for you. And you might want to print this in color as well. If you have a color printer at home, that would be helpful. And you'll notice here, you can see, as I was saying, the value of b is the same in both forms. And essentially, what we're doing here when we're changing from exponential to logarithmic form is we're isolating the value of x. In other words, x becomes by itself on one side of the equation. And that's the whole point. The purpose of a logarithm is to be able to solve for that exponent. Okay? The base raised to the exponent gives us a certain result or a certain answer. Okay? And so what we're doing here is we're switching around the situation so whatever that exponent is actually becomes our answer over here. And here's a perfect example with actual numbers again. We've got 3 to the 4th power equals 81. And we can see here what we did is we have log base 3 of 81 equals 4. So we're just taking that 4 and putting it by itself on one side of the equation. And again, you'll see it in some examples in a few minutes. Okay, so first thing we're going to do here is we're going to zoom back out a little bit. We are going to solve exponential equations with the same base on both sides to start with here. And we're going to see how easily we can solve these without using logarithms because they have the same base on both sides of the equation. And then we're going to end this lesson by seeing exponential equations that don't have the same base on both sides and how we'll need logarithms for those. Okay, so very simply here you can see, 3 to the x equals 9, and you all know how to solve this. What you're thinking is, to what exponent do we need to raise 3 to get 9? Okay, and all of you can easily answer that. You know that 3 squared equals 9, so we know the answer is x is equal to 2. So this we were able to easily solve without using logarithms at all. Okay, but to help us relate this to a logarithm, just on this first example I'll show you. Okay, so let's look at how we can relate this to a logarithm. Again, we are saying that logs are the way we can solve for the exponents. Okay, so if we change this to logarithmic form, let's see what happens. What we can do is we can rewrite this. We can make the x that's up here by itself on one side of the equation, okay? We're gonna say log base. You can see the base up here is 3. Let's just highlight this so you can kind of see the relationships. So here we've got the base is 3, and here's the base is 3. So those are the same value. And once I fill in this information, I've put the exponent by itself on one side of the equation. I've written the word log, and I've written the base. The only value that's left over that I haven't used is the 9, okay? And so that 9 ends up here, okay? And you can go back and you can look at the concept summary above and see how it relates in general to how we go from exponential to logarithmic form, okay? So in this case, what you get out of this is that if I were evaluating this, if I wanted to later on, we'll be evaluating logarithms that look like this, I would say to myself, what number do I have to raise 3 to get 9? And that answer would be 2. And so when I evaluate this, I get x equals 2, okay? Now, when you're actually solving these equations, we don't have to do this for every one. I just did it for this first one so you can see the relationship between exponential equations and logarithms, okay? So let's go to this second one here, for the x equals 64, okay? Now I'm going to do something on this one that I didn't do on part A because I want you to be able to easily do part C, okay? So what I'm going to do is I'm going to rewrite both sides of the equation with the same base. And what I'm saying that base is, of course, you can see is 4, okay? So if I rewrite 64 with a base of 4, if you think to yourself, what power do you have to raise 4 to get 64, you would know that that is 3. So we could say that 64 is 4 cubed. Now, of course, if I want both sides of the equation to be equal, immediately then we can match up these powers and we can see that x here is the same as 3. And we would just say that x equals 3, okay? So up here I was doing it mentally. Here I wrote out the powers. You can do it either way. So the advantage of the way I did it in part B is it'll help us figure out how to do part C, okay? So in part C, I've got a very similar equation to part B, but only 64 is in the denominator. Well, I can still write 64 as a power of 4. And we all know that if you have 1 over 4 cubed, it's the same as 4 to the negative 3. And so immediately then I can match these up in a similar way that I did in part B, and I know that x has to equal negative 3, okay? And finally, let's look at part D here. We've got 5 to the x is equal to 1. And again, mentally, most of you know, I hope, that when you raise any number to a certain power, you'll get 1, and that certain power is going to be 0. We know 5 to the 0 will equal 1. But you can also do this. You know, if I want to write 1 with the same base as I have on the left side of the equation, I write it with a base of 5 and a power of 0. And again, x would equal 0. Okay? So as I said, these were relatively straightforward because they had the same base on both sides of the equation. Later on, we'll see ones that don't have the same base on both sides of the equation. Okay? We're going to look at specific types of logarithms here. We're going to be looking at common logarithms and natural logarithms. And we'll see in a few minutes when we evaluate these that we've seen these before on our calculators. But before we do that, let's just kind of go through. We know here that the base 10 logarithm is called the common logarithm, and it's written as log x. In other words, we don't actually have to write that number in the basement. Remember up here, we wrote the base of 3 in the basement because it was in base 3. Here, because we're base 10, that 10 is understood, and we actually don't even have to write it. It's understood without being written, okay? The base E logarithm, remember E, we used it, for example, in continuously compounded interest where we had the PERT formula, A equals P e to the RT. That is called the natural logarithm, just like base E was the natural base. And it's written ln, and it stands for log natural, or natural log of x, with a base of E understood without being written, okay? So in other words, you can see log base 10 of x means the same as log x. The 10's understood. It's not wrong to write it. It's just we don't typically write it that way. Log base E of x means the same as natural log x, ln x. Okay, and if you want, you can pause and you can look at your calculator and find those buttons on the left side of your calculator. One thing I want to point out to you is when you are doing your Pearson assignment, there's a question there that involves natural logarithm when you have to type in ln as part of your answer. If you type in log base E, the program will mark it wrong. Okay, so yes, it's perfectly correct to write log base E, but we typically write natural log. And since the program is designed to write natural log, just make sure of that. If you write log base E in your work, just make sure when you type it in that you do ln of x. Okay. All right, so we're going to do example 2 here. We're going to be converting between exponential and logarithmic forms. And when we're done with this page, then I'd suggest that you do number 1 to 16 of your 6-3 Pearson assignment. Pause the video at that point and then go on to the rest after you've done those first 16 questions. That way you can kind of break it up for yourself. Okay? So we're going to look here at rewriting exponential equations in logarithmic form. And again, we're going to just review what we've already been talking about here. We can see we've got the base here. And here is the exponent. Okay. Now, again, the exponent is going to be the same as the logarithm. So if I want to write this in logarithmic form, I know that I want to get 2 by itself. So that's the number I already know is going to be by itself on one side of the equation. I also know that my base is going to remain the same. So I can go ahead and write the word log and put that number right there in the basement. And then if I look at my original exponential equation, the only value that's left is the 9. And so I'm going to write 9. Okay? And so this is considered my logarithmic form. And again, later on, we're going to be looking at evaluating. You're going to have to take an expression like this and be able to figure out that the answer is 2. Because we say to ourselves, what number do we have to raise 3 to get 9? And the answer is 2. Okay? Now, I want to remind you, at any point in this video, you can pause and you can try the next problem and then continue the video and see if you got it right. That's a good way to kind of simulate what we do sometime in the classroom, where I ask you to take out your whiteboards and do a problem to check it, and then we check it together. I would suggest you do that here. You know, it doesn't have to be on a whiteboard, on paper, anything. Just try them on your own before you see me work them out, and then you'll feel more confident. Okay? So if we get to this point here, you know, think about to yourself, what value is the base? What value is the exponent? You know that the exponent is the value of the log, so that's the number that's going to be by itself on one side of the equation. Then we write log. We say to ourselves, well, what's the base here? It's going to remain the base. And then we fill in the other number. It's relatively straightforward. And again, the way we read this is log base 7 of 343 equals 2. Okay. In this example, we know that the exponent here is -2. And so we can notice also that the base is 6. So we've got log base 6 is going to equal -2, and the only number that's left is that 1/36, and we fill that in, and we're done with that one, okay? And finally here on this row, 2 to the 4th power is 16. We've got log base 2. We know that the exponent is the value of the log. The log is equal to 4. And we fill in the 16. Right? And we know 2 to the 4th power is 16. You can kind of, you know, when you're checking your answer, you can kind of draw arrows for yourself like this. 2 to the 4th power equals 16. Okay. All right, so now we come down here, and in this row, you'll notice we have some special bases. You've got base E here, dealing with the natural base, which are going to relate to natural logarithms. And we have base 10, which deal with the base 10 or common logarithms, okay? So first thing I'm going to do is I'm going to do this exactly like I did in up here, okay? I'm going to say log. I know the log is the exponent, so I'm going to put that here and on the other side of the equation. I can see the base is E, so I'll write that down here. And the number, the answer that I had, goes here, 7.3891. But that's not my final answer because, as I said, we don't typically write log base E. It's not wrong to, but again, if you typed it in this way on the computer in your Pearson program, it's going to mark it wrong. So you have to write it as ln, okay? So I'm going to write ln in place of log base E of 7.3891 equals 2, okay? So again, log base E is the same as ln, but we want to typically write our answer as ln, and we read it natural log of 7.3891 equals 2. Okay? All right. So we want to notice here of special value. We notice that we've got e to the 0 equals 1, which makes perfect sense. We know any number raised to the 0 power equals 1. Okay? So if we change this to logarithmic form, we'll get log base E equals, the exponent is 0, and the number that we haven't included yet is that 1. So we have log base E of 1 equals 0, or natural log of 1 equals 0. Okay? So this is a special value. We'll highlight it a little bit later when we continue, but this is important for you to notice here, that basically that anytime we take log of 1, we're always going to get 0, because any number to the 0 power is 1. It doesn't matter if it's natural log, common log, or log to any other base. It doesn't make any difference. Anytime we take log of 1, we're going to get 0. So that would be a note that you want to make, and we'll emphasize it again later too, that the log of 1 equals 0, and that would be true with any base at all. So I'll put a box there to emphasize that's true with any base at all. Log of 1 will always be 0 because any base to the 0 power is 1. Okay? Let's look here at 10 cubed is 100. Okay, so here again we've got base 10. As I said, we're looking here at common logarithms. So when I put this in logarithmic form, log base 10, there's your base. The exponent is a value of the logarithm, so that 3 is going to go on the other side. The number I haven't used is the 100. But again, log base 10, that 10 is understood. Okay? So typically, I don't want to write it. So I'm going to say log of 100 equals 3. And I will leave out the 10 when I write my answer. Okay? So let's look again, finally, and one more converting from exponential to logarithmic form. Log base 10 of 100 1,000 equals -3. I'm doing this one a little bit more quickly because hopefully at this point we've done a number of these. You should be able to figure that out. So again, here's the base, here's the exponent, and here's the value that's remaining. Okay? And we're going to know that base 10 is understood, so we're going to say log of 1/1000th equals -3. Okay. All right, so we're going to rewrite the logarithmic equations now in exponential form. We're just going to go backwards here. Okay. Now you'll notice we have a situation where we don't have a base rating. So you want to think about that and say, you know, what type of logarithm is the base understood when we see the word log? If you look right back up here, you see, oh, it's base 10. So we know that we're going to put in, we can put a base 10 in here. Okay. And then if I want to change this to exponential form, here's my base. And the value of the log is the exponent. So I'll write 10 to the 5th power equals 100,000. Okay. If we look here, we've got log of 1/100th is equal to -2. Again, let's put that understood base 10 in there. Now, we're not always going to have to put that understood base 10 in there. You're not always going to have to write it because you'll get used to it and you'll immediately be able to write the exponential form without doing that. But for right now, I'm filling it in for you. And we'll say 10 to the -2 equals 1/100. Okay? And actually, I could leave out those parentheses here. You know, these are optional. So I could have just said, I can point that out and we can leave them all. Either way, it doesn't make any difference. Okay, so just 10 to the -2 equals 1/100. Okay. And we're doing a lot of these, and you know the advantage of doing this as a recording is if you feel like you're starting to get the hang of it, you can always fast forward through this, right? So if this is starting to become like, oh, I got this, you could fast forward through it if you feel comfortable. Although I wouldn't fast forward through the next row here because in this, then you're going to be looking at some different bases. All right, so with this one though, we've got log of 1/1000th equals -3. Again, I can put in that understood base 10 there. Okay, so we know we've got that base 10 understood. I'm going to say 10 to the -3 is equal to 1/1000. Okay. All right, so now with just some different bases here, again, recognize here's the base. The value of the log is the exponent. Okay. And I haven't been highlighting too much here. Maybe I'll highlight these just to make sure we all got it. Okay, so here's the base. Here's the exponent. And here's the value we're taking the log of. Okay, so if I put them down here, I've got 4 squared equals 16. So you can see where everything went. Here's the base. Here's the exponent. And here's our answer. Okay. All right, 2 more, and then I'd suggest that you pause the video. It's going to be, you're not going to want to listen any longer. It's going to be too long. Okay. So we've got on this one here, you can see the base, and here you can see the exponent. And so we can say 5 to the 3rd power equals 125. And also here, we've got a natural log situation. So when we have, in this particular case, what I would do to get this into exponential form is to first rewrite this as log base e of 1 equals 0. Okay, this is kind of the opposite of part F in example 2, part 1. So if we go back up to that example up here, you'll notice that we started out with e to the 0 equals 1. I wrote it as log base e, and then I converted that to ln, natural log, and vice versa here. What I would do is start with that natural log form, rewrite it as log base e to get it in, to help me get it into exponential form. And now I can see here the base, the log is the exponent, and so I can say the base is e, the exponent is 0, and the answer is 1. Okay, so as I said, this is where I suggest that you pause the video and do numbers 1 to 16 of the 6-3 Pearson assignment, and that way you'll be able to kind of break it up and not have to take too much information in at once. Okay, I'm going to continue, but I would suggest at this point that you pause the video. Okay, and then of course you'll finish the rest of them. There's 36 questions, so you'll finish 17 to 36 after you have completed the rest of the notes. Okay. All right, so let's continue. Some of you may have already done numbers 1 to 16 now. Let's look at how we can look at the fact that an exponential function is the inverse of a logarithmic function. Okay, so what we're going to do is we're going to write the inverse of each exponential function, which basically means we're going to change these equations to logarithmic form. Okay, now let's just go back and remember how we write inverses of any kind of function: exponential function, linear function, quadratic function. Let's remind ourselves of the steps. Okay, so number 1, we know we're going to exchange x and y. Now, I did not put these in function notation, so you won't have to, worry about changing f of x to y here. I started out with the y just to make it simpler. But we know when we find the inverse, we're going to exchange x and y. And then after we've exchanged x and y, we solve for y. Okay? But in this case, solving for y will mean changing to logarithmic form, because that's how we're going to get we're going to be able to get that exponent by itself on one side of the equation. Okay, so let's go ahead and do that. So we're going to exchange x and y. So we're going to put x by itself, and we're going to say x is equal to 2 to the y. So that's number 1. And then number 2, we're going to change to logarithmic form. So basically, we're going to do exactly what we had just been doing, where we converted from exponential to logarithmic form, only this time we're dealing with variables instead of constants. Only difference. Okay? So I'm going to say log, the base I can see is 2. And the exponent is equal to y. Remember, the log equals the exponent. The number that we haven't used yet is the x. And so solving for y is just a matter of changing from exponential to logarithmic form. And this is the inverse of the original equation. So these two equations are inverses of one another. Okay? So we're going to do the same thing here. We're going to exchange x and y and solve for y. Okay? And so I'll exchange x and y here, and I'll get x equals 4 to the y. And I'll do the same thing as I did in number 2. Now, if you want, you can pause this and see if you can get it before I continue. So you could pause right here. And now I'll continue. we want to get y by itself on one side of the equation. You can write it on either side. I happen to keep it on the same side on the right. Log base 4 of x equals y. The y is the value of the exponent. Here's the base, here's the x. Okay, and again, I'll highlight this so we can kind of see where everything is coming from. There's our x. Here's the base. And the exponent is here. So, right there. Okay. Again, I would suggest you try to do this one on your own and then continue the video. Okay. So we have y equals 9 to the x. Again, I want to exchange x and y. So I'm going to exchange x and y. So I'll put the x over here and the y over here. And then solving for y is a matter of just putting it into logarithmic form. Log base 9 of x equals y. We're done. Okay. And notice here, in this particular case, I happen to make the base a variable, not specific number. But it doesn't matter. Just recognize this is the base. It's still the base. This is still the exponent, which is going to be the value of the log. Okay. So we're going to exchange x and y. We'll have x is equal to a to the y. And we're going to solve for y. So again, y is going to be by itself. Here's the base, and here's the x. Okay. All right. If you want, you can pause the video to try to absorb what we just did. I'm also posting questions separate from the assignment on writing the inverse, because there are no questions in the assignment on Pearson that relate to this example 3. So you'll be seeing a separate post for that, where I'm not going to count it specifically as an assignment, but it'll be extra practice, which I'd encourage you to do, because it will be on the quiz that we're going to be doing at the end of the week. Okay. Example 4, part 1, we're going to evaluate logarithms without a calculator. Okay. So what we want to do, you'll notice here we don't have an equation, we just have an expression. What we want to do to be able to evaluate logarithms is we're actually going to make them into an equation. I'm going to set each of those expressions, these expressions, equal to x. And then to be able to evaluate them, I'm going to change to exponential form. And then I'm going to use mental math to solve for x. Okay. So first of all, let's rewrite this equation. We know that there's no base that we see, but when we don't see a base, we know it's understood to be a 10. So I'm going to rewrite this as log base 10 of 10 is equal to x. Okay. And I'm going to now change to exponential form. So if I change it to exponential form, the base is 10, the log is the exponent, it's going to equal 10. And mental math will tell me that x has to equal 1. Okay? So I'm using mental math now to solve for x, and I can see that x is equal to 1. So we're basically solving equations very similar to what we did in example 1. We were just solving exponential equations that have the same base on both sides. okay? Let's look at part B, natural log of E, okay? So natural log of E, again, I'm gonna set this expression equal to X to make it into an equation. I'm also going to rewrite this. I'm going to write log base E of E equals X to make it easier for myself to be able to change it to exponential form. And now I'll go through the 2 steps, changing it to exponential form. So I've got E to the X is equal to E. And again, I'm going to get X is equal to 1. Okay. Now I want you to notice something special about A and B here. I want you to notice that we're taking the log of a certain value, and that certain value happens to be the same as the base. And their answer we're getting is X equals 1. Notice over here, we're taking the log of a certain value, it happens to be the same as the base, and the answer we're getting is 1. So what you want to conclude here is that when you take the log of a value and that value is the same as the base, you're always going to get an answer of 1. And that's because if you take that base, the power that you have to raise to get that same number as an answer always has to be 1. E to the first power is E, 10 to the first power is 10, and it'll work with any other numbers as well. Okay. Let's look at this one where we've got log of 0. Let's see what happens here. I'm going to fill in the understood base here, base 10. We've got log base 10 of 0 equals X. Now, if I rewrite this in exponential form, I get 10 to the X is equal to 0. And then if I want to do the mental math now, and I say to myself, well, what number do I have to raise 10 to get 0? So I'm going to pause for a moment. I want you to think about that. What number do I have to raise 10 to get 0? And what you should be thinking is this is impossible. And so what we're going to say is the answer is undefined. Anytime we take log of 0, it's going to be undefined. Okay, and if you're not exactly clear why, let's just kind of go back and remember a little bit about what we learned before the break. Remember, we graphed exponential functions. So if I have this expression as a function, y equals 10 to the x, okay, that's basically y is equal to b to the x, where the base is 10. Remember, if I graph this, it would basically look like this, with a y-intercept at 0, 1, right? When x is 0, y is 1. And you'd have an asymptote at y equals 0. So you will never reach 0. And therefore, 10 to the x could never equal 0. Okay? So that's a critical piece that we'll emphasize again before we finish this lesson. Okay? That when we take the log of 0, we're always going to get a value that's undefined, regardless of which base it is. It could be base 3, base 100, base 1,000, base 65. It doesn't matter. Okay. We'll look here at a value log of 1. Okay. Log of 1 is equal to x. This is actually the natural log of 1, so I'm going to rewrite this as log base e of 1 equals x. If I rewrite that in exponential form, I will get 1 is equal to e to the x. And if I think about it, if I want to figure out what number I have to raise e to get 1, of course, that's going to be 0, right? E to the 0 equals 1. So I want you to notice here what we came up with. The natural log of 1 was equal to 0. So if the natural log of 1 is equal to 0, we can kind of extend that to actually any base. Because regardless of what this base was here, to get the answer 1, the exponent would have to be 0. So for any base whatsoever, it doesn't matter. The log of any base, I'm putting a box there to represent any base, log of 1 is always equal to 0. Okay, and again, that's something you want to definitely take note of. It's going to be really, something that you might see on your quiz, for example, at the end of the week. Okay. So try this one on your own for a moment before you continue the video. So I'm going to say equals x. And again, I know that I've got an understood base 10 here, so I can fill in that understood base 10. And to figure out the value of x, I'm going to change it to exponential form. So I know that 100 is equal to 10 to the x. And of course, the answer I get here, if I think to myself, what number do I have to raise 10 to get 100? The answer is 2. Okay, so I know that my answer to this question is 2. And in fact, you don't have to write x is equal to 2. You can just write 2 because we were just writing the x in for purposes of changing to exponential form to ultimately get the answer. But technically, if I said to you, what is log of 100? You could just tell me 2. You don't have to say x equals 2. Okay? So kind of on that note here, when we do f, log of 1 over 100, I want you to try to do this one a little bit more mentally. Okay? So I'll still fill in the base here. But, let's see if you can kind of figure this out a little bit mentally. You know that 10 to the second power, if we kind of think of there is an x here, you can kind of imagine there, that 10 to the x is equal to 1 over 100. We know that 10 squared is 100. So think to yourself, what would be the answer here? If the answer here was 2, what's the answer here? Well, your answer you should have gotten is -2. And I'm hoping you were able to figure that out mentally. If not, we can put this in exponential form. We know that 1/100th is equal to 10 to the x. I can rewrite 100 as 10 squared. And then rewrite 1 over 10 squared as 10 to the -2. And so then we'll end up with -2 is equal to x. Okay? And so the answer here, as we just said a minute ago, was -2. Okay? Okay. So for this one, let's see if we can do this one a little bit more mentally. Okay, again, I want to tell you what you should be thinking so we can maybe do some of these without having to do all this work every single time. Again, I could say equals x here, but I want you to try to do this a little bit mentally. So let's try mental math. So I want you to think, what number do we raise 3 to get 9? And the answer, of course, is 2. Okay? Now, if you worked this out using the methods we were just doing by changing to exponential form, you should still have gotten the same result. but it's useful to be able to use mental math instead. Okay. All right, here. So let's look at this one. We've got natural log of e to the 9th. Okay. So I'm going to go back because this one is a little bit more complicated than log base 3 of 9. I'm going to go back and we'll do it the method we were just doing, changing to exponential form, because I want you to notice something. Okay. So let's rewrite this as natural log as log base e of e to the 9th equals x, because remember, natural log is the same as log base e. Okay. And let's rewrite this in exponential form. So we can see here, here's our base, and the value of the log is going to be the exponent. So I'm going to write e to the x is equal to, here's the e to the 9th, we'll just bring that down right here, e to the 9th. So e to the 9th equals e to the x, and then it's very easy to match those up, and we can see that x is equal to 9. Okay, so here's another special situation to notice. If you have a situation where you're taking the log of a power, in other words, you have another exponent in here that you're taking, that's part of the value that you're taking the log of. Notice that if the base of that power that you're taking the log of is the same as the base of the log, your answer is whatever that exponent is. You notice we've got there's the 9s, they match up. So whenever you're taking whatever the values of the base are, if the bases here match, the answer is whatever that exponent is. Okay. Log base 5 of 1/25. Again, at this point, many of you can do this on your own, so try it. I'm doing a lot of examples here, especially since we're not in school. That way you have lots of examples to check, so you can always pause. But I definitely would make sure that you stay tuned for J, K, and L, because those are special situations there, again, that you want to make sure that you're familiar with. Okay? All right, so we've got log base 5 of 1/25, and I'm going to set that equal to x. Now I could say to myself, what power do I have to raise 5 to get 1/25? And many of you can do that mentally, because you know you have to raise 5 to the 2nd power to get 25. So then think, what power do you have to raise 5 to get 1/25? Okay, many of you already know the answer. So I'll write 1/25 equals 5 to the x. So this is 1/5 squared equals 5 to the x. So I'll rewrite this as 5 to the -2 equals 5 to the x. So as many of you already came up with, the answer is -2. Okay. Okay. So finally, the last set of questions where we're evaluating logarithms. So log base 7 of 7. Okay. So again, I want you to try this using some mental math. Okay. Think to yourself, what number do you have to raise 7 to get 7? Okay. What number do you have to raise 7 to get 7? If you want, remember, go back up here, look at parts A and B, and remember what we talked about, that if the base of the log matches the number you're taking the log of, what's always the answer? So we have that same situation here. The base of the log is the same as the value we're taking the log of. So 7 to what power is 7? You can see the answer is 1. And again, to verify it the longer way, we can write it in exponential form. 7 That's this 7 right here we're looking at, okay? Equals, this is this 7 over here, the base, and the log is the exponent. And as you can see, of course, the answer is 1. Okay? Now, for this one here, here's a special situation that you definitely have to pay careful attention to. Okay? Let's say equal to x here, because I need to try to figure out a number where if I raise 7 to some value, I will get -7. So let's look at that. Here's the base, here's the exponent, and I want the answer to be -7. Okay. So again, I'm going to draw a little sketch, just like I did up here for the base 10, and I'm going to basically make it look very similar, where again, you're going to have that y-intercept of 1. So if I look at that sketch, let's consider that this is y equals 7 to the x. The y-intercept here again would be 1, because 7 to the 0 is 1. And you'll notice that the y values are never negative, because again of that horizontal asymptote at y equals 0. So if the answer can never be negative, log base 7 of -7 is impossible. And therefore what we say is it's undefined, okay? And in general, just like we had a general rule up here, log of 1 is equal to 0, here's another general rule that we have to be aware of, that regardless of the base, log, regardless of the base of a negative number, is always going to be undefined. Okay? That's another rule that we want to make sure we're aware of. You can't take the log of a negative, because you can't raise a base to any value and get a negative result. Okay? Okay, last one here, and then again, I might suggest you pause the video again just to take a break, because these are long, these aren't designed to all be done in one day. If we were in school, I'd probably do this lesson over the course of 3 days. But I'm just making one video in this case because I'm home. All right, so let's consider we have the same type of situation as we've had previously. So you want to try to think about, mentally, what number do I have to raise 5 to get 5 to the 9th power? Okay, what number do you have to raise 5 to get 5 to the 9th? The answer should be obvious. The answer is 9. Okay, and again, if you want to work it out, do that. 5 to the 9th will equal, here's your base, it's right here. 5 to the 9th is equal to 5 to the log is the exponent is x. So x has to equal 9. But again, mental math tells you, what number do you have to raise 5 to get 5 to the 9th? Obviously 9. So again, it goes back to that rule we were talking about, that if the base of the log matches the base of a power, just like up here in part H, where the base e's matched, so the answer was 9. Here the bases of 5 matched, so the answer is 9. Okay? All right, so take a break if you need to, or if not, continue, whatever works for you. Okay, so we're on the last part of this lesson, and I think next time I might break up into 2 videos, because this even gets long for me here, but you all, like I said, can pause. I'm going to continue. So we're going to continue now. We're going to evaluate logarithms now with your calculator. And I want you to specifically look at the log and natural log buttons. And this is going to go very, very quickly. Here I'm just going to show you very easily how you can use your calculator to get your answers. Okay, so if you don't have your graphing calculator out, go ahead and get it. If for some reason you left your graphing calculator in your locker, I want you to remember that we do have apps that you can use to be able to get a graphing calculator on your phone. Also, when you're doing this on Pearson, you'll be able to find in the tools section a graphing calculator on the Pearson site that you could use as well, okay? Or any scientific calculator has a log and LN button as well, okay? All right, so let's look at how we would just calculate log of 1,000, okay? So using the graphing calculator that you're familiar with, on the left side, you can see log and LN, and if you're using this type of calculator, of course, you're going to type log first and then put the number that you're taking the log of, okay? And as you can see here on your calculator, log is the inverse of 10 to the x, and that's why they go together. One is the second function of the other. Similarly, we had seen it before when we were looking at e to the x, and we were looking at just exponential functions before the break. Ln is the inverse. Natural log is the inverse of e to the x, so it's right below it. So if I want to just take log of 1,000, I'll hit log first, and then just type 1,000. And then just hit equals, okay? And you can see it said round to the nearest 10,000th if necessary. Obviously, in this particular case, there's no rounding necessary. And you know, this is one we could have done by mental math also, because you want to remember, you have an understood base 10 here, and we know that what number do we have to raise 10 to get 1,000, and that is 3, okay? So many of you mentally could come up with this answer too, but we can check it in our calculator, right? Because you know if log of 1,000 is 3, think about what log of 1 over 1,000 would have to be, okay? So let's try that. If I take log of 1 divided by 1,000, I will get, as we would expect, -3. Okay? Now, log of 900. Here's where you have to use the calculator, because I would doubt that any of you would be able to come up with a value, you know, other than maybe approximating of what number you'd have to raise 10 to get 900, because it's not an integer value, it's a decimal, which is why we're saying round to the nearest 10,000. So if I take log of 900, we've got 2.9542. Now I said round to the nearest 10,000, which means 4 decimal places. Remember, you've got tenths, hundredths, thousandths, 10,000ths would be where that 2 is. So we'd say the answer is 2.9542. That would be to the nearest 10,000th. Okay. Now what you want to notice, by the way, is, you know, the calculator is designed to easily calculate when we have log base 10 or log base e, but there's not a direct on your buttons way to get logs of other bases. We're going to learn later on how to calculate easily logs of other bases, and I will actually show you a calculator trick where you have to go into one of the menus to get logs of other bases as well. Okay, so natural log of 1, you can imagine what you would do there. You just hit natural log button and then hit 1 and then hit enter. And you can see you will get 0. Again, that's back to a rule that we were just talking about. If you take the log of with any base of 1, it's always going to be 0, because any number to the 0 power gives you 1. Okay? So again, if you haven't already written it down, I'm going to write it down again just in case. This is a rule you've got to be clear about. Log of any base of 1 is always going to equal 0. Okay? Log of 0. Do you remember what happens there? Think about what happens. What number happens if I try to raise some base to a power to try to get 0? Think about that graph and what we just talked about. Okay, now look at what happens when I put it in my calculator. Log of 0, log or natural log, it doesn't matter. Any log base of 0, look what happens. The calculator gives me an error. Okay, your answer is not error. Okay, this is your calculator output. Your calculator output is error. That is not your answer. Okay, you have to say the word undefined. That is your answer. Okay. Now you got this complicated looking natural log of negative 1.895. But again, think about that graph we were looking at. Okay, think about if I have, no matter what base I give you here, if I raise a base to a certain power, can I get a negative result? Okay, look at what happens. If I take natural log of negative 1.895, enter, of course we get an error. And again, you're not going to say error. You're going to say your answer is undefined. Okay. Finally, we are at the last part of the lesson here. Again, hopefully you took some pauses as you went through this. We're going to solve equations using common and natural logarithms. We're going to figure out what the solution is to each equation. I guess there should be a question mark here. We're going to then round to the nearest thousandth. Okay, so this time we're going to go to 3 decimal places. So nearest 10,000th here, we did 4 decimal places. Here, nearest thousandth, we'll go 3 decimal places. Always pay attention to that, especially like when you're doing the online. You know, you might think you have the right answer, and if you just rounded to the wrong decimal places, the computer's going to mark it wrong. So make sure that you go to the correct number of decimal places. Okay. So we're going to look here at solving exponential equations, just like what we were looking at the very beginning of this lesson, but this time the bases are not the same. Okay. So now that we know about logarithms, what we can do to be able to solve is we're going to solve by changing to logarithmic form. Okay. And in this lesson right now, we're going to specifically leave our equations to ones that are either common logarithms, which are the base 10 log, or natural logarithms, which are base e. Okay. Later on in a later section, we'll look at solving exponential equations and logarithmic equations that are not common or natural logarithms that are in other bases. Okay, but here we want to use ones where we'll be able to use our calculator. So we're going to solve by changing to logarithmic form, because as you can see here, if I were going to try to solve for the exponent, I can't write 25 with a base of 10. And so I can't make the bases the same on both sides, so I can't match up the exponents to solve for x. And so what I'm going to do is I'm going to change to logarithmic form. That's going to be my key. And what we're going to do when we change to logarithmic form, of course, we want to pay attention to what the base is. And we want to pay attention to the exponent, because we know that the exponent is the value of the log, right? And so I can write x minus 1 immediately by itself on one side of the equation, because we know that's the whole point of this, is that I want to say that the log is equal to the value of that exponent. My base is 10, And then the other number that's left is the 25. So now I've written this in logarithmic form. Now the left side might look a little bit ugly, but I want to remember that base 10 is understood. So all I need to do is rewrite this as log 25 equals x minus 1. And before I tell you, think for a moment, maybe pause and think about, how can I easily get log of 25? And hopefully you thought about it and you said, oh, you know what? I can just go on my calculator and type log of 25, and I can figure out what that decimal is. Okay. So if we do that by saying log of 25, I have, remember, I want my answer to the nearest thousand. So I'm gonna go out to like 4 decimals. Make sure I don't get any rounding error. I want to round to the nearest thousandth at the end. So I'm going to say 1.3979. Okay. So I've got 1.3979 equals x minus 1. And of course, if I just add 1 to both sides of the equation, that's going to give me my final value of x. Okay. And so the final value of x that I get is x is equal to, and when I add 1, I'll get 2.3978, but I said to round to the nearest thousandth, which is 3 decimal places. So I'm going to say 2.398. I rounded the 7 up to the 8. Okay, and that's the value of x. Okay. Now, when you're first doing these, be sure to check. The easiest way to check is literally put this right back up here. You put that in your calculator. 2.398 minus 1 will give you 1.398. If you put in your calculator 10 to the 1.398, let's see what we get. 10 to the 1.398. Hit enter, and you can see I just get just about 25. Again, I rounded, so it's not exact, but I know I did the correct, I got the correct answer. Okay. All right, let's look at the next one here. Again, I want to solve this equation by isolating the exponent and set it equal to a logarithm. Okay, so I'm going to say the log is equal to x plus 2, okay? The base is e, and the number that's left that I haven't used is the 8. So we're going to say log base e of 8 is equal to x plus 2. I'll rewrite that as natural log of 8 is equal to x plus 2. Now, you can go ahead and do this on your calculator. I'm just going to write out, now I've shown you the calculator functionality. I'll just write what I calculated. I got 2.0794 equals x plus 2. I can then subtract 2 from both sides, and rounding to the nearest thousandth, I'll get 0.079 as my answer. And again, check that and make sure you get the right result. Okay. Let's think about how we might work this one here. You'll notice what's different about this one is you have a coefficient in front of the power. The key to this is you need to make sure that you isolate the power first before changing to logarithmic form. So isolate the power and then change to log form. Okay. So we're going to go ahead and we're going to isolate the power. You notice we're multiplying by 2.25. So we're going to divide by 2.25 to get e to the x plus 2 by itself. Okay. So if I do the division there, I'm going to get 12.6222. The 2 just continually repeats. I just went out to 4 decimal places there. So I isolated the power. That's what I did here. Okay. Now we're going to change to log form, okay? So I'm going to say x plus 2 equals log base e of 12.6222. Again, log base e is the same as natural log of 12.6222. When you put this in your calculator, you will get x plus 2 equals 2.53546. And if I subtract 2 and round to 3 decimal places, I'll get 0.535. Okay. Okay, we're going to go back and see how knowing how to work with logarithms can help us solve for time when we're dealing with compound interest. Okay. We're going to look at how long does it take for $325 to double at 3% annual percentage rate compounded continuously. Okay, and we're going to round to the nearest year. So you want to remember, compounded continuously means that A is equal to P times E to the RT. Okay. Remember that P stands for how much money you had at the beginning of your principal, so that would be $325. I want to know how long it takes to double. So that means that my final amount is going to be 325 times 2, because I'm doubling, or $650. My interest rate is 3%, or 0.03. Okay, so I'm going to substitute these values in. Now the key is I don't know how long it's going to take, so I'm looking for the time. So let's substitute what we have. We've got 650 equals 325 e to the 0.03 t. Okay. Now if we go back to what we just did in part C, remember we want to isolate the power. So I'm going to divide both sides by 325. Now, if I divide both sides by 325, notice what happens. I get 2 equals e to the 0.03 t. So there's something interesting to note here. You notice here how that 2 relates to the word double. And just in case you see a question like this in the future, you can notice that it doesn't matter what we even started with. If I want to just find out how long it's going to take my money to double at 3% interest compounded continuously, I don't even have to know how much I started with. It's going to take the same amount of time regardless of what I started with, because I could have put, for example, 1,000 as my final amount and 500 as my principal. 1,000 divided by 500 would have given me 2. It doesn't make any difference. So to double, I put a 2 here. To triple, I put a 3 here, and so forth. Okay? Now, what you would have probably done in the past before the spring break to answer this question, you would have maybe done some trial and error. But now we can actually change to logarithmic form to be able to solve for t. Okay? So I'm going to change to log form, and that way I don't have to do guess and check. Okay, so I can write 0.03t to isolate that exponent. That's logarithm equal to log. The base is e, and the number I haven't used yet is the 2. So log base e of 2 is equal to 0.03t. Okay. Now I'm going to rewrite log base e as natural log, right? So natural log of 2 equals 0.03t. And now it's just a matter of calculating natural log of 2 in my calculator and then dividing by 0.03 to find the time. Okay? So we'll just do that over here. The natural log of 2 in my calculator to 4 decimal places came out to 0.6931. equals 0.03t. And when I divide, I find that t is equal to 23.10, and the decimal continues there. But notice, pay attention to where we need to round to, especially when you're using that computer program, Pearson. You want to pay attention to these details. So round to the nearest year, so I'm going to say that that's going to take approximately 23 years to double my money. Okay? Now, last but not least in this lesson, we are going to solve logarithmic equations. Again, only dealing with natural and common logarithms, and we're going to do that by changing to exponential form. Okay? So remember, first of all, that we can rewrite natural log as log base e. And then I'm going to change to exponential form. So I'll rewrite this as 2x plus 3 is equal to e to the fourth. Okay? Now this is where you want to remember from before the break on your calculator, you right above ln, you've got the e to the power button. You've also got an e above the division sign. So to get e to the fourth, all I do is I hit second ln, gives me e, and I can fill in the power 4, enter, and I got e to the fourth power. Okay, now for this, I'm going to go out to, I might as well go out to the 5 because to make sure I'm as accurate as possible. So 54.59815 is what I'll write. Equals 2x plus 3. And I'm then going to solve. I'm going to subtract 3, of course. So I'll get 2x equals 51.59815, and then divide by 2, and x is equal to, and I'm going to go back to the directions at the beginning before we did the compound interest problem. We want to go to the nearest thousandth, so I'll go out to 3 decimal places. When I divide that out, you can check it on your own calculator. I got 25.799. Okay, 2 more, everybody. Stay with me. This one, we've got that understood base 10. Log base 10 of 3x minus 2 is equal to 2. Okay. I'm going to rewrite in exponential form. 3x minus 2 equals 10 squared. So 3x minus 2, this one's easy to do in our head, equals 100. Add 2. We'll get 3x equals 102. And this one actually divides in evenly, so we don't have to round. 102 divided by 3 gives us 34. Okay. And then last but not least, okay, this one I put on here particularly because I want to remind you, remember up here that we can't take the log of a negative, okay? It's undefined. In fact, we can go back up here and just kind of emphasize that. Log of a negative is always going to be undefined. We said that on the prior page also, right? We know log of a negative is undefined, okay? And we know also that the log of 0 is also undefined. So these are our rules that we want to be aware of to be sure we know. And we said log of 1 is 0, okay? But going back to the log of a negative is undefined. Don't confuse that with this last situation here, okay? Here we're saying the log is equal to a negative. What that's saying is that the exponent is negative, and that's okay. Okay, you can have a negative exponent. So that negative number is not inside parentheses, and so this is acceptable. It's not undefined. So make sure you distinguish the negative in parentheses, undefined, negative equal to the log, okay. So we're just going to remember this is base 10. I'm going to rewrite this as log base 10 of x minus 2 equals negative 2. I'm going to put that in exponential form. X minus 2 equals 10 to the negative 2. Now, I know many of you would be inclined to just use your calculator at this point, but I want you to think about what this means instead of always running to your calculator. This is 1 over 10 squared, right? And we know that 1 over 10 squared is 1/100th, right? So you can do that in your head. There's no reason to have to jump to your calculator just because you see something that looks a little bit ugly. So that's 1/100th, and because I'm looking for decimal answers here, remember we said we're going to the nearest thousands, I'm going to just write that as a decimal. 1/100th is 0.01. Then if I add 2, my answer is actually exact, so I don't even have to round to the nearest thousandth here. I can just take it right to the 100th place because it's an exact result. Okay? Well, that's it, everybody. Now you may finish the 6-3 Pearson assignment. Okay? Thank you for listening, and I hope you're having a great day. Bye-bye.